Okay, let's get started. So I give you a chance to exit this talk right at the beginning. So I have a very big title of low-level system programming in a high-level language. The title could have also been building a platform for AI in Julia. The title could have also been building a database, a compiler, and an ML framework in Julia. So if these things are not what you think you signed up for, it doesn't hurt my feelings for you to go to another talk. Okay, so I'm Mohan Arif. I work for Relational AI. It's a small company of about 23 people full-time. We also have a faculty network of another dozen or so faculty that work with us part-time across a variety of universities in the US and Canada and Western Europe. And we're working on something called Relational AI. So I feel like I have to take a couple of minutes to set the stage for AI here. So we think that artificial intelligence is the next big opportunity. I know it's super hyped, and I know that there's a tendency to roll your eyes sometimes when you hear about AI, because there are hundreds of companies that are claiming to be doing AI, and not every one of them is doing something very deep. But I think that AI is emerging as a general purpose technology that's going to have a transformative effect on our world in the same way that semiconductors did 50 years ago, and in the same way that the internet did about 25 years ago. Okay? There's a book that came out recently called Prediction Machines that talks about the economic argument for AI, and basically talks about the semiconductor revolution in terms of a dramatic drop in the cost of arithmetic. The internet is a dramatic drop in the cost of search and distribution of digital information. And AI is about a dramatic drop in the cost of prediction, because prediction, as you see the Jan LeCun quote here, is the essence of intelligence. If I'm driving a car and I want to decide if should I go left or go right, I predict the outcome of what will happen if I go left or go right, and then based on that prediction, I make a decision. Okay, so anticipating the future is the essence of intelligence. Okay. All right. Let me define AI technically, a little bit more technically. Okay, so DARPA has been one of the great funding agencies behind AI for many years. They just a few months ago put out a new program announcement for something called AIE, and copied verbatim from that announcement. It says, past DARPA AI investment facilitated the advancement of first wave or rule-based and second wave statistical learning-based AI technologies. Okay? DARPA-funded R&D enabled some of the first successes in AI, such as expert systems and search, and more recently has advanced machine learning algorithms and hardware. So DARPA is now interested in researching and developing third wave AI theory and applications that address the limitations of the first and second wave technologies. Okay, so that's, I'm trying to sell you on this by appealing to authority here. If you don't know who I am, but hopefully many of you know who DARPA is, and they funded innovations like the internet and GPS and the AI first and second wave and many such innovations, and so hopefully their word carries some weight with you. So just very quickly, first wave AI was all about rules and relations. It's based on one of the great pillars of mathematics and science. It's based on logic. And the idea in first wave AI is you learn from expertise. You sit down with a physician or a lawyer, you ask them questions about how they make a certain decision, you capture their thinking in a set of rules, and then you do inference by using these rules in situations you haven't seen before. This is great in managing complexity and learning from expertise, but doesn't do so well when you have uncertainty, right? When things are fuzzy and the rules might conflict with each other, okay? And these kinds of systems historically are built in or on or produce languages like Lisp and Prolog and Datalog and variants thereof. Second wave machine learning is based on another important pillar of mathematics and science, which is probability. Not all machine learning systems give you a probabilistically interpretable answer, but somewhere in the bowels is heavy use of probability and statistics. The idea here is you learn from examples. And deep learning is sort of the poster child of this community because, thanks to the internet, we've been able to collect lots and lots of examples of images and speech and text. And deep learning has done very well in terms of building models that can make predictions about what's in those images and speech and text and so on. Deep learning has also been really good at playing games because games like Go and chess can be played by computers against themselves billions of times, and so you can generate an infinite set of examples that you can just basically brute force your way through and learn something about the game. And machine learning is really good at managing uncertainty, although as you'll see in a minute, it's not so good with structure. It's very, very flat in the way it looks at things. And systems that do second-wave machine learning are usually built in combination languages like Python or C or R and C, or in ML frameworks like TensorFlow and PyTorch. Okay, so what does third wave AI then? What's it going to look like? Is it going to look like the first wave or the second wave? There is no universally agreed upon strategy here. One approach would be to continue the connectionist approach or the neural network-based approach and build more and more capability with that as a foundation. Jan LeCun, who's head of research at Facebook, AI research at Facebook, and many others believe that's the path to artificial general intelligence. Others believe that the approach should be sort of a hybrid symbolic and statistical approach. And within that community, you actually have sub-communities like people who believe probabilistic programming languages are going to get you there, people like Josh Tannenbaum at MIT and many others. And then others that believe that statistical relational learning, things that combine logic and probability directly, are going to be the way forward. People like Pedro Domingos and many others also believe this as well. Okay, so I can't tell you for sure which approach is going to end up dominating, but I can tell you for sure that we're placing our bets on probably the least popular of these approaches, which is the approach that combines logic and probability together. It combines symbolic logic with statistical reasoning. Okay? And so a lot of what we're doing in relational AI is building a rule engine and a relational data management engine on the one hand, and an ML framework on the other. Okay? And so looking at the requirements of both and using one to help the other and vice versa. All right, so what's how are we going to know that third wave AI works or is an improvement? Well, here are 5 dimensions to improvement. One dimension is accuracy. Can we build more and more accurate models that are better and more accurate predicting the future? Another criteria is understandability. Can we build models that humans can understand? Third criteria is versatility. Can we build models that basically go from everything we know and then can make inferences about things we don't know, can go in any direction, which is not something that, for example, first and second wave systems do. Can we build models that are robust? So that work really well in situations where we don't have a lot of examples and don't have a lot of expertise. And somehow a little bit of expertise and a few examples kind of work together to give you good predictions and good decisions that you make based on those predictions. And then a 5th criteria is, can we build models that are fair? Models that aren't going to be prejudiced in some way that we don't want them to be prejudiced. Okay? And what I'm here to argue to all of you today is that all of these problems are computational problems. Really, sort of the underlying capability that you need to do all these things better is all about performance, okay? High speed and efficiency and so on. So fairness is a computational problem. Explainability and understandability is a computational problem. I glossed over it in the previous slide, but DARPA, for example, is sponsoring a program on explainable AI where some of the researchers working on the program, I believe from MIT, are building deep learning networks to explain the behavior of other deep learning networks. And so you have now twice as much or more needed for computation to kind of build the explainability into the other. Okay? Fairness, again, is very much an issue like that, and accuracy. A lot of models today make assumptions around independence of examples and so on that are rarely true in reality, but they do so because it's computationally expensive not to do them. Okay, so in this world of rules and relations and in this world of probability and statistics, how you get performance? Well, you get performance in this world just like how you get it in any other world. There are generally two approaches. One approach is all about reducing the amount of work you have to do, just do less work. And that's all about picking algorithms that have lower asymptotic complexity than other algorithms. A merge sort is better than a double sort because one is n log n and the other is n squared. Okay. And in this branch of the tree, you can take two branches at least here. One is, and we're going to be talking more about this branch, is to specialize or to build algorithms that are specialized for and exploit problem structure. So problems might have algebraic structure. There might be sort of by algebraic, I mean mathematical algebra here, so there might be group structure, or semi-ring structure, or ring structure that you can take advantage of to do less work. Or combinatorial structure. For those of you who know databases and study this, a fractional hypotree width of a particular query, for example, is combinatorial structure, or statistical structure, or geometric structure, and so on. The other way to do less work, and there might be more, is to basically take a really hard problem and map it to a tractable problem, solve the tractable problem, and then use the answer to the tractable problem as a way of approximating the answer to the hard problem. Okay, and there's a lot of really cool work being done in this area, specifically in the context of machine learning, techniques like variational inference and a variety of flavors and so on. Okay, so our high-level language, in this case Julia, should make it easy to implement algorithms like this and facilitate that, okay, and make it possible to implement sophisticated algorithms without jumping through hoops. Okay, the next branch, or if we pop up to sort of the first fork in the tree here, is instead of focusing on doing less work, which I would argue is the most important branch, is to do the same amount of work but to do it faster. Okay, and there are, I think, 3 buckets usually that these kinds of optimizations fall into. These sort of constant factor optimizations. One is all about latency hiding. So memory hierarchies are getting quite complex, and so manage your memory hierarchy down so that when you get the data you're working on closer and closer to your CPU or your computer, to do more with it and not to kind of thrash around memory and so on. So being able to process data in sequential order, for example, and avoiding random access is a common way of managing and hiding latency. Okay, in the database world, a few years ago, it became very popular to have in-memory databases that basically took all the data that up until then was residing on disks and collapsed out one level of the memory hierarchy by moving it all in memory. Okay. Similarly, parallelization is another such strategy. So on a single core, you have SIMD instructions now that can do the same instruction on a bunch of values. You have multiple cores that you can do, again, throw more labor at the problem. And then you have accelerators that you can think of as having many more cores, whereas a GPU can often have 65,000 teeny cores on it, so it's super parallelization in a sense, and then TPUs and eventually FPGAs and so on. And then the third bucket for doing sort of constant factor optimizations is specialization. So databases, compilers, ML frameworks are designed to solve a very broad range of problems. A database has to answer any query expressed in SQL. And so you write an interpreter that can answer any query in SQL. But at some point, you actually see the query, okay? And now, in most cases, you pay the price of that generality of the system when evaluating that query. Well, what if you knew the workload and the data set at compile time? Wouldn't you want to sort of specialize the query evaluation and underlying data structures to take advantage of that knowledge, okay, and not pay for the overhead? Okay, so let's go and give you a little bit of intuition about the do less work, or the brains. I call these sort of two approaches brains over brawn, because this is about being clever, and doing the same amount of work faster is all about brute force, GPUs and memory and all that kind of stuff. Okay, so let's look at brains a little bit. So remember, we're doing third wave AI, and our approach is to take the investment that humanity has made over the last 40 years in building, for example, relational databases that are based on relations and logic, the same kind of stuff that rule-based systems are based on, building models and schemas and ontologies that represent specific domains in the enterprise, curating data and loading and maintaining and managing data sets in these databases, okay? And I would argue that these kinds of databases have actually made second wave AI possible, because without this data, you wouldn't have the examples that you would learn from in the second wave AI. All right, but ironically, what's the first thing that you do when you go to build predictive models from relational databases? You start off with data in a schema like this. You build a feature extraction query that then generates a very flat table, one table that might have 1 billion rows in it. It might have 1,000 columns or 10,000 or 100,000 columns, where each row is an example, is an instance, and each column is a feature that you're going to feed into a statistical model. Okay? And the irony of all of this is that after going to all that effort to build that structure, you then go, these joins in the feature extraction query are a lot of effort to throw it all away, to flatten it all out, to get rid of all the structure, to put it in a design matrix. Okay? And that domain knowledge, okay, has to be rediscovered by the underlying machine learning algorithm by running optimization, a very expensive thing mathematical. Okay, so obviously this does not sit well with me anyways. And as you'll see in a minute, the situation is actually much worse than that, because if I'm, for example, building a model to predict sales of smartphones, one of the features I might use is the brand of the smartphone. The smartphone is an Apple, but a smartphone could be Google, or it could be Samsung, or it could be Motorola. And statistical techniques don't know how to deal with symbolic information like Apple and Motorola and so on. And so you have to do something called, something like one-hot encoding, which is to take this information and then for the brand column, let's say you have 4 or 5 possible brands, you would create one column for Apple that will be 0 or 1, one column for Google that will be 0 or 1, one column for Motorola that will be 0 and 1, and one column for Samsung, and so on. Okay, so that expands the data sets even further and making it harder and harder for the optimization to find patterns. The other really annoying thing when you destroy all the structure is like this phone is an Apple, whether it's sold in store 1 or store 2 or store 3 or store 10 or store 1,000. Okay, it's always an Apple. Relationally, this is represented very compactly. In this design matrix, I will see this information repeated over and over and over again. So if I have 1,000 days of history and 1,000 stores, this fact that this phone is an Apple might be repeated 1,000,000 times. Okay? And then similarly, there will be attributes of store that don't vary by product or time that will be repeated for every product and day. And there will be attributes of day that don't vary by store or location, by store or product, that will be repeated by the cross product of those two. And that's extremely, extremely inefficient. Okay? So, and then after you created this sort of really fat design matrix, then you would run the optimization on it. All right, so let's revisit this from first principles. Again, let's do Elon Musk type move here. So ideally, if we do this the right way, we would want to avoid materializing the join. We want to avoid one-hot encoding. We want to exploit the relational structure to speed up learning. And we want to do this in much less time than it takes to even produce the design matrix, okay? So we want to actually build the whole model in less time than it takes to create the design matrix, okay? So a database person would look at this problem and say, interesting, this design matrix is just a view on this underlying relational database. And relational databases are really good at pushing work through joins. So if I have 2 really big tables that I can join together and then filter the result, or I can filter both tables and then join them together, the latter is a much more efficient way than the former, because when I'm joining 2 big tables and then filtering the results, I'm basically throwing away a lot of work I'm doing to do the join that I don't need, because I'm going to only keep people whose middle initial is X. Okay? And so in the same way that in relational databases you can take a filtering operation and push it through the join and end up doing a lot less work, we can do the same with gradient descent and stochastic gradient and batch gradient descent optimizations. We can push the optimization that's needed for machine learning through the query that defines the feature matrix and actually have the optimization run on the underlying much more compact relational structure. In fact, we don't even need to look at the relational data more than once, because what we can do is actually summarize it, aggregate it, and only have the optimization work over the aggregate or summary information. Now, this doesn't work for every kind of machine learning method, but it works for a lot. It works for supervised and unsupervised methods. It works for deep methods, not necessarily traditional ReLU-based deep learning networks, but deep sum product networks. It works for regression methods, classification. So there's a broad range of methods that this works for. Okay, and in the interest of time, I won't dwell on this because I still want to get to sort of the Julia implementation aspects of this. The number of aggregates that you create obviously can vary by the kind of model class that you're running. And the way that you create the summary information can be done in a very clever way where you're not scanning the underlying data over and over and over again, right? So if I have a sales data by item, by store, by day, which is very big, as you'll see in a minute, I don't have to keep aggregating from that. I can aggregate that to maybe month style and then use that aggregate information to create more aggregate information and other aggregate information. So I don't always have to go from the raw base data to produce these summary bits of information. Okay, so let me just give you a quick example of this. This is a data set that comes from the Kaggle competition. Kaggle is sort of a company that Google bought that's sort of where people can publish data sets and pose problems for people in machine learning to work with. So this is an open data set. This data set is organized relationally this way. I have inventory that's keyed by store, date, item, okay? And then an amount of inventory, amount of units. And I can join in the inventory information about stores, like the zip code of the store, the size of the store, and so on. I can join in the inventory information about the items, like the brand and the category and the price. I can join into this, here is implicit information about time, like the day of week and the day of month and so on, and the month of year. And then I have, because I have weather information, weather determines demand, because if the weather is bad, people stay at home and don't go shopping. I have information that's by store, date, that tells me whether the weather was good or not that day. Okay? And then for store, I have zip code, and zip code can be joined to get me demographic information about the people that shop in that store. Okay? I've been working in this field for about 30 years. I've spent 25 years of it in retail. Retail models are never this simple. They're actually much, much more complicated. They have way more structure than this. But we're going to just accept this as a realistic example and show you the impact even on this realistic example. So these five tables are inventory table where most of the information is held, 84 million records. If you exported that from Postgres, it would be about 2 gigabytes in a CSV file. Then I have 5,600 items. I have 1,300 stores. I have 1,300 records containing demographic information and 1.1 million records around weather. And all this data together, if you just sort of export it in a relational form and round up, let's say, takes about 2.1 gigabytes of storage. Okay, this is before I run the query that joins it all together to produce the design matrix. Okay, if I run that query to produce one table from those 5 tables, I would end up with a table that has 84 million records, so it's going to have as many records as sort of the biggest one of those. It's going to have 44 columns in it, 3 of which are key, which are the location, or the store, the item, and the date. And it's going to blow up from being 2.1 gigabytes in size to 23 gigabytes now. Okay, and this is actually before the one-hot encoding. Okay, one-hot encoding is going to blow that up even more. And producing this just join on Postgres running on one of our laptops took 217 seconds just to join all that stuff together. And then exporting it from Postgres so that we can feed it in TensorFlow took another 373 seconds. And then building a very, very basic linear regression model that used 40 of these columns as features to predict the 41st column, okay, which is like, say, inventory or sales. And doing that in TensorFlow with just one epoch, running a million records at a time. Okay, so we have 84 million records, so it would do 84 iterations to do just one pass on the data set to produce a linear regression model. It took over 1,200 seconds. Okay? Now, let's do it sort of the right way, or our way. In our way, you have relational data, it's 2.1 gigabytes, it's the same amount of data. I don't have to join it together, so I don't expand it. I don't have to export it, so I don't have to do that. I do have to aggregate it to create summary information. That takes about 18 seconds because I'm clever about how I aggregate it. And it condenses, the summary information condenses all the 2.1 gigabytes to 37 kilobytes. This 37 kilobytes is what you're going to be iterating on when you're doing the gradient descent. Okay, and so parameter learning, which is iterating over these iterating over these 37 kilobytes, takes half a second. Okay, so building the first rev of the model using these 40 features goes down from 12,500 seconds to 18.5 seconds. And then every model thereafter, okay, because these aggregates don't change, takes half a second to build. Okay, so the first model is 676 times faster. Every model thereafter is 24,000 times faster. Okay, and every model thereafter, it could be that I start off with 40 features, and I'm going to say, okay, give me a subset of these features to see how well I do. So 39 features, 38 features, 40, 30 features, etc. And so now searching feature space can happen half a second at a time instead of happening 12,000 seconds at a time. And so you can do a much better job of searching feature space. You can do a much better job of building graphic models. Okay, we did this again for a Yelp data set, and in the Yelp case, the 284 megabytes of relational data blew up into 42 gigabytes. And in our case, it's summarized or aggregated into 2.3 gigabytes. And then here are sort of the relative times. Okay, so what? So, you know, as we know, Moore's law up until now, anyways, it sort of gives you a doubling every doubling every 1.5 years. GPUs, for example, that are now kind of considered fundamental to doing anything in AI and machine learning, according to NVIDIA's website, give you a 2 to 10x performance boost. So 2 to 10x is about 3 doublings, a little more than 3 doublings. So 4.5 to 5 years of Moore's law, okay, by using GPUs. Okay, well here we are getting 1,000x or more than 1,000x speed up, and so effectively 1,000x speed up is a 15-year advantage of Moore's law. Okay, and you can take all this sort of performance and speed, and you can use it to get more accuracy and understandability and so on. Okay, so let's get to sort of the second half of this, which is where we dig into how we use Julia more specifically. So this is about doing the same amount of work faster. And this is about, you know, abstraction without regret. And again, as a quick reminder, this is about managing your latencies well, parallelizing well, and specializing your code well. And I think, as you know, you'd expect, primary motivation here for us is time and money. Okay, so we don't have infinite time. The AI world is moving quickly. There are much bigger companies that are doing this sort of stuff, and so we want to be able to move quickly as well. And so we don't have the money to hire 100 engineers to do something. And you know, if you do it with sort of a group our size, we don't have you know, the amount of time. For example, it took us to build a prior system in a prior company that did less than the system we're trying to build here. It took us 3.5 years to build it in C++, and that system did a really good job of latency hiding, did a really good job of parallelization, but it didn't try to do any kind of specialization. Okay, and for us, specializing code means jitting it, it means LLVM, and all sorts of engineering complexity that, you know, would have added, we think, significant engineering time to the 3 to 5 years. All right, so when we started looking at how we're going to do this implementation, we looked at sort of where you normally look. So we had a lot of experience with C++. We knew that was the devil we knew. We knew that we could make it work in C++. We were also intrigued by Rust. So Rust sort of is a cool language that has a lot of cool features that would have eliminated certain classes of errors. So we looked at that. We also looked at techniques, emerging techniques coming out of the PL community around multi-stage programming, libraries like LMS and Squid that use Scala as the programming language, or the programming language with a rich type system that would, you know, in principle, let you write a SQL interpreter that can be specialized for a particular query. And kind of in the last minute, one of our colleagues, Jamie Brendan, who was doing some consulting for us, said, hey, why don't we look at Julia? He had sort of blogged about using Julia to implement a data log query engine. And we said, okay, let's look at it. Jamie, we'll give you a month or two, I don't remember. We'll build a POC in Julia, we'll build one in Rust. We knew how to do this in C++. We had someone on the team, a couple of people on the team that had sort of done this in multi-stage programming libraries in Scala. So we built a couple of prototypes. And after the allotted period of time, we had just gotten much further and had done more in Julia than we had done in these other languages. And frankly, this wasn't an easy thing for us to observe because quite a few of us were pretty sure that we were going to find out that, say, something like Rust was going to be productive and performant, and that something like Julia wasn't going to be. Okay? And it just wasn't the case. The data did not support that bias. So, being the scientist that we are, question?
Do you mind if I ask a question?
Yes.
Do you remember the sort of multiples, like how did Rust compare to Julia compared to C++ for performance?
I don't remember. I'd rather give you, since this is being recorded, I'd rather give you an accurate answer than a fast answer.
Sure.
But there was a difference, and it wasn't clear. And after spending that time in Rust, one of the things that wasn't clear to us is how good Rust and its type system would be in sort of in a JIT mode. There were a couple of early attempts at using Rust to do just-in-time compilation and queries and so on, but it wasn't clear that the community had worked out how to do that without a ton of engineering. Okay? Whereas in Julia, we kind of got that for free. And I'm going to explain what we did here in a minute. Okay? So again, nothing against Rust or C++ or Scala and Squid. These are all great languages, but for our set of trade-offs, this is what made sense for us. Okay? I don't know how much you all know about Julia. So I have my one slide overview of Julia. I think Jeff Bezenson is in the audience, and he'll be giving a talk about Julia right after this one next door. I don't know that he's going to really introduce Julia either, but you can hear more about Julia in his talk in 30 minutes. The Julia community likes to describe Julia as a language that looks like Python, feels like Lisp, and runs like C. Those are not my words. This is a words that sort of come from the community. And if you go to the julialang.org, you find the description that says Julia is fast, dynamic, optionally typed, and multiple or multi-dispatched. And it feels like Lisp because it supports features like hygienic macros, code quoting, and generated functions. And it runs like C because it has it specializes code, Julia code that you write, based on sophisticated type inference for specific types that will be there at runtime. And it does inlining and unboxing and uses LLVM to generate assembly dynamically. Very, very late in the game, for us, as people who are not going to see the query until, our system has been in production for a while, and the user is going to give us the query very late in the game here. We're not going to see the data sets until our systems are in production. So it sort of lets us specialize late in the game. So I'm going to show you 4 examples of this. None of this work is work done by me, so I might not get the details exactly right, but I have some colleagues here that might be able to help you with the details. And some of this is reflected back in open source libraries that you can go and look at. So one example is around, around sort of doing the same amount of work faster around latency hiding is building memory hierarchy-friendly data structures. So the database community uses data structures like B+ trees, which have high fan-out, so you don't have to go do a lot of random accesses in memory, or compressed column vectors, or LSM trees, etc., to manage latency in memory hierarchy. Okay, and in a lot of situations, these data structures are paged, and you want to be able to sort of page them out to disk, and then page them back into memory as you need them. Okay, and so you want to eliminate as much effort as possible in doing this sort of deserialization, and you certainly don't want to have to parse and unpack these structures after you bring them into memory to be able to access the information that you have on them. Okay, and so this is we're implementing something called the Epsilon Tree. Details don't matter. It's kind of like a B tree that's optimized for for rights. This is the actual Julia code, I'm told, that we implemented to implement a node in that Epsilon tree. So you have a vector of messages, a vector of pivots, a vector of children that are identified by page ID, and then some summary statistics that go with that page. Okay? And so what we want to do is be able to, after we bring a page into memory, just be able to access it without having to further parse it and further unpack it in memory. Okay, so our colleague and Jamie implemented a library called blobs.jl. You can think of it as sort of our variant of flat buffers, or I think Apache Arrow. It lets you do this kind of thing without having to dynamically allocate memory and copy data from this data structure node into a structure that Julia can then work with. Okay? The way that Julia supports us doing this is after, if you go out and look at blobs.jl. So everywhere, this is the same structure I showed you before with one difference. Everywhere I have a reference, I replace the reference with the blob version of that reference. So I have blob vector and blob instead of vector and nothing. And the Julia machinery basically does all the work to compile all the overhead away. So for example, if I do a size, which is a standard Julia operation, on a dereference of the children in a particular node, we've overloaded the dereference operation to recognize the fact that you're working on a blob data structure. And Julia will basically sort of eliminate the overhead involved and give us the answer. And to kind of convince you a little bit that this is really true, we ran a quick experiment here on a vector with 1 million elements and timed it to see how long it takes to sort it and how many allocations are generated, how many dynamic memory allocations generated when you sort it. And it takes 9.3 milliseconds. And then we did the same thing on the blob variant of it. And as you can see, it took roughly the same amount of time, and it did 2 dynamic memory allocations in the process. Okay? If this wasn't being done correctly and you had to sort of do a dynamic memory allocation per tuple, it would have been very, very, very expensive. Okay, so this is a big win, allows us to do something fairly low level, something that you couldn't even do in Java until very recently, and you can do it in Java today, but in a very cumbersome, low level way. And we would have thought that you needed something like a Rust or a C++ to do this before. Okay, next example is for query evaluation. So you might or might not know that until very recently, being the last 5 years, most databases in the world interpreted the SQL that you give them. It wasn't compiled. IBM in the late 70s and early 80s tried to implement an early version of DB2 so that it compiled SQL down to machine code. And the engineering effort involved was so high, and it was so hard to support this kind of approach across different machine architectures that they basically gave up on it. And then they convinced the rest of the industry to give up on it as well. And 30 years go by before people attempted to revisit this, because the performance of SQL for many applications is not very good, and people were looking to make it faster by specializing in and compiling it. Okay, so if you've worked with AWS, for example, and you use Redshift, Redshift is an example of a database that attempts to do query compilation, but it does it in a very clumsy way, I think. It takes a SQL query and compiles it down to a bunch of C++ code as text, emits that text to a file, then calls GCC on that file, then gets the binaries that are produced by GCC, and then calls into those binaries. Okay, you can imagine what a nightmare that is in many ways. It's a nightmare to develop, it's a nightmare to debug, it's a nightmare to support. It's just a nightmare. Okay, and of course the compilation times involved are very, very high. More enlightened approaches that have become more popular recently sort of use this sort of multi-stage programming technique and so on. And for us, Julia represented sort of a very nice point in that design space because we felt like we could write a compiler that would take a SQL query and compile it down to Julia, and then let Julia do sort of the rest of the specialization for us and capitalize on Jeff's and the Julia community's work in that area, so that we're not doing all the work from them. Okay, and I kind of glossed over it. I shouldn't have. Let me show you. this is sort of how the compilation chain works in Julia. You start off with Julia source code, you parse it, you get a Julia AST, you lower that to Julia IR, you compile that into LLVM then you compile that further to machine code, which executes, which can in turn generate more Julia AST, and then you can keep going. Okay, so our job is just basically to produce something out here, and then let Julia do the rest. Okay, so in order to prove that to ourselves, we didn't start by writing the SQL to Julia compiler. We started by taking SQL snippets like this. This is kind of a small piece of a very popular query used to benchmark SQL databases from a benchmark suite called the TPCH benchmark suite. So we sort of hand compile this down to this Julia code. So ideally, this SQL query would generate this Julia code, and then let Julia then run on that, do its thing on that. And from that, Julia emitted this machine code. Okay, and then we ran that on some data sets and showed that actually it runs really, really fast, especially if we design the data structures in a way that is compatible with this approach. Okay, and in fact, LLVM simplifies this code if we wanted it to, and so if we have our code stored neatly in columns and so on, we get simplification for free from LLVM. Okay, so that's very, very, very cool. And so now the challenge becomes, can we build a compiler from SQL that emits this kind of Julia code? Okay, and how do we want to build that compiler? Do we want to do that in Julia, or do we want to do that in Java, or something else? And so we evaluated Julia as a compiler construction language. And so that's sort of the next quick case study here. Well, the TLDR here is we found it to be quite good for compiler construction. Okay, again, sort of leveraging this sort of abstract, it has all these great abstractions that it can compile away and give us a high performance compiler. Okay, the two features of Julia that come in really handy for this are multiple dispatch, and so we can avoid sort of the visitor pattern that you see in a lot of OO languages or OOish languages like Java and Python. And then pattern matching and generic transversals implemented in the Stratego style, okay, by using macros and the meta programming constructs in Julia. Okay, and so there was a macro library called match.gl that didn't quite do what we wanted, that we implemented as rematch.gl because the person who created match.gl was not sort of taking our feature requests. And we put that out there just like the blobs library. It's out there in the open source, and you can play around with it. And then we're working on a second library that will probably open source that will be kind of stratego.jl. It's not named yet, but this library that will let you do generic traversals in the same way that you can Stratego, so that you don't have to write a lot of boilerplate. Okay, so a lot of work that a compiler does is traversing an abstract syntax tree and transforming it as it traverses it. Again, as I said earlier, we exploit sort of Julia's support for multiple dispatch to do this very efficiently and very concisely. And there are two ways to kind of traverse, two techniques to traverse this abstract syntax tree. One is sort of the handwritten approach, the explicit approach, and then the other is the generic general approach, which is you just write a general top-down traversal of an AST, or bottom-up traversal of an AST, or Stratego supports something called the innermost traversal of an AST that keeps sort of running over the AST until you can't do any more transformations. Okay? And so if you have a general traversal strategy, you combine that with a set of rules of what to do when you hit a node. Like, for example, you can say a not of X is really X, or an and of an or left distributes, or an and of something and an or right distributes, and so on. Okay? So the general approach to doing this sort of requires you to implement these sort of top-down, bottom-up, innermost once, and then a set of rules for the language that you're implementing in the compile. Okay, so this is the this kind of thing, we implemented this kind of thing sort of three ways. Once in Java using the visitor pattern. We didn't do the generic way in Java because that was just too painful. And then once in Python, where we implemented it with the visitor pattern as well as the generic traversal. And then we did it in Julia both ways as well. And you can see Julia sort of improves slightly on the the other two languages because it has this sort of multi-dispatch, and we don't need to implement the visitor pattern to kind of implement multi-dispatch in terms of two single dispatches. Okay, well, how well does this run? So in Java, the handwritten visitor approach takes about 0.01 seconds. Like I said, we didn't try the generic approach because that was just too painful. In Python, the handwritten visitor approach takes 0.3 seconds, 0.36 seconds, which is maybe acceptable, but maybe not. That's 36 times faster than the Java, slower than the Java approach. The generic traversal, although it was very compact, was basically infeasible. This benchmark here was just traversing an AST that has 2 million nodes in it, and that would have just taken 9 seconds just to traverse it. Okay? We did this in Julia, again, a handwritten way that uses multiple dispatch, took 0.04 seconds without really spending any time thinking about how to optimize that. We also implemented naively the generic traversal, and initially it wasn't type stable, which is Julia parlance, means that we couldn't do the appropriate kind of type inference that would let us sort of specialize the code and emit good JIT code. And that took 2.1 seconds. But then when we made it type stable, it went down to 0.09 seconds the first time, and then 0.07 seconds every time thereafter. And so that difference in 0.02 seconds or 20 milliseconds the first time is the time it took to compile the Julia code down to assembly code to do that. Okay? And to kind of make this all come together, here's a slightly more involved example that has sort of the generic traversals as we implemented them in Julia, combined with a couple of approaches to transform code, a rule set that does simplification, that does things like the not of x is x, and of anything in true is that thing. It also does more involved transformations like implementing the distribution laws for and over ors, or ors over and, or nots over any expression. And this is useful to create sort of, to take a logical statement and transform it into disjunctive normal form or conjunctive normal form. And so this is the actual Julia code that does all of that. And so I can call the innermost on an EST that simplifies, then distributes and over or, and then distributes knots, and keep kind of doing that until it reaches fixed point, and I would get the output would be sort of the DNF version of that EST. Okay. Last very quick example is something that we had to do sort of in a painful way in a prior experience around adding rich data types to our database engine. So, for example, if you wanted to add imaginary numbers, or you wanted to add something even more pedantic like fixed precision decimals, because as you know, floating point numbers have round-off issues that make them sort of unworkable for financial calculations. Okay, I don't need to go into that. So the sort of, one of our academic collaborators in faculty network is a gentleman called Peter Bonch. He's implemented some of the fastest databases on the planet. Really, really smart guy. He's kind of always implemented them in a traditional way. And the traditional way to implement database support for fixed decimals is that you basically write your query engine to work with integers, and then at the SQL level, you rewrite sort of the fixed decimal thing as you rewrite it as an operation on integers, so that by the time the query hit your database engine, all it saw was integer operations. Okay, which is makes the code messier and makes it hard to modularize. And so what we did here is we ran an experiment where we took sort of the standard fixed decimal library from Julia, and we used that basically as the data type, and convinced ourselves that we can do this efficiently because Julia will compile away a lot of the unboxing and whatever overheads associated with using a type implemented that way. And so this is fixed decimal. It's parameterized in terms of some integer and the number of decimal points you want in your answer, and that gives you something that's a subset of the reals. Here is a kind of a constructor for it, if you will, and here is an implementation of the addition of two fixed point numbers, and so you convert them into integers, you add them together, and then you take that and pass that to reinterpret, which gives you back a fixed point decimal. So normally there's a lot of kind of overhead associated with this approach, and in fact, this is what happens here. One of the nice things about the Julia REPL is you can see the machine code that's emitted when you run it, and these are all the the 3 or 4 or 5 instructions that you get that sort of compile away all this memory. Okay? All right, so I've talked about latency hiding and specialization and the value of those and the way they'll simplify our own engineering and the way they'll give us performance in our compiler / database engine / ML framework. What I haven't talked about is parallelization and acceleration. And this area, when we did our prototype way back when, 9 months ago now, when we first started doing this, was an area where we thought that Julia needed to be improved. And the great thing about the Julia community is we were able to kind of reach out to Jeff and company and say, hey, tell us about your plans for improving multi-threaded support and implementing sort of what's in the documentation here efficiently. And in the Julia community and the Julia developers that were busy working on releasing Julia Julia version 1, which was released in August, I believe. And with that out of the way, now that the Julia community has a sort of a stable language to work from, implementing something like this becomes the priority. And so we expect some early variant of this support to come out in the next few months, and then hopefully in the next 6 to 9 months, it will go from being sort of early support for high-performance multi-threading to fairly mature support for high-performance multi-threading. And there have been multiple bits of work that were done that take Julia code and generate GPU implementations of said Julia code. And so I make reference to one of those papers. And then recently, Kino was one of the Julia developers, co-published or co-wrote a paper that shows how you can take Julia code and emit TPU code, which is an even more specialized accelerator than GPUs that Google has implemented. Okay, so I can't tell you hand on heart that we've done this and know that this will work, but we're very encouraged by what we've seen so far, and we think that, again, Julia's investment in multi-threading and GPU support and TPU support and eventually other kinds of accelerator support will be, we believe, will be something that we can leverage and will be work that we won't have to do as we build our database compiler / ML framework. Okay, so in conclusion, we think that so far we're very happy with our choice, and we think that I don't know if Jeff and the Julia guys did this and girls did this by design or not, but I think it's a great language for systems programming as well, not just scientific computing and numerical computing, as I think was the original aspiration for the language. Okay, and I tried to use a version 1 logo here instead of the version 0.6, but they've since taken a fresh approach to technical computing out of the banner. So
why do you think we took that out?
Because of our work, obviously. Because they don't want to kind of pigeonhole themselves to just technical computing. Okay, very quickly, again, I want to emphasize that I'm kind of the village idiot in our company, and this is work that's done by a lot of my very accomplished colleagues. You can find references to the details of that work in these papers on worst-case optimal join algorithms, which is a class of join algorithm that after people working in database join algorithms for 3 decades, now my colleagues were able to invent that show that you can actually implement database joins in an asymptotically optimal way, worst-case optimal way. So that was a big breakthrough that we built on. Another breakthrough is on building query plan optimizers that work with these worst-case optimal joins to produce query plans, okay, that are also worst-case optimal. Okay, and a lot of things in machine learning require both the worst-case optimal joins as well as this kind of query optimization to get the asymptotic complexity results that we're getting. Then there's a lot of cool work by my colleagues and others to do this in-database or relational learning, this kind of learning that gives you the 3 orders of magnitude speed up for some data sets or more, that exploits the relational structure, exploits first-wave AI, exploits all this information that people have built over the years into relational databases, and by the way, also into object and class oriented programs or functional programs or semi-structured data like JSON data. All of that stuff has structure that you can exploit in the same way. Our focus has been on relational data sets, but the underlying math is the same. So here are some papers that sort of describe that. And then finally, papers by the Julia community, two actually are published in this USLA that either have had talks or will have talks. I've lost track of when these talks are going on, that describe some of the internals of Julia and how it's implemented. So with that, I thank you, and I can take some questions. No questions is good too.
Towards the beginning of the talk, you said that fairness, among the other attributes mentioned, was also computational. And I was just wondering if you could elaborate on that a little bit further.
Sure. You can naively think that you can build fair models in AI by not including features that are directly gender or ethnicity or race or age or other ways that you can have undesirable bias. But that's not good enough, okay? Because you can have other bits of information that correlate very highly with those features. And so there's an inherent tension between fairness and accuracy. And if you want accuracy in the sort of mathematical sense, sometimes you can achieve it by taking these kinds of factors into consideration, and you get more accurate models, but not models that you want to run your business on or run your life on. And so understanding and detecting these correlations between, say, age and other input that you have in your variable, like college degree, for example, or where you live, or, I live in Tampa, Florida, might imply that I'm older than, I'm living somewhere else. And so understanding those correlations is a computational problem. Now, people have studied this more deeply than I'm addressing here, and just like with explainability, explaining the answer, which kind of helps you also address the fairness in your model, because if in your explanation for the answer you say, oh, I looked at a person's ethnicity or gender or something like that, and you say, oh, no, don't do that. Or I looked at a variable that correlates highly with one of those things. As I mentioned earlier, explainability is a computational problem because a lot of people are solving explainability by building models that explain the underlying. All right, thank you very much.